Good afternoon. So this is the session where I think the people from the West Coast start to flag and the jet lag starts kicking in. And therefore, fitting to this, we will have two talks from USC. Actually, the original program says there were 3 talks in this session, but unfortunately, Costa from NASA, he had issues with his visa and couldn't attend. But now we will have an invited talk from Walter Vinci from University of Southern California.
Thank you very much. First, let me thank the organizers for giving me the opportunity to give this talk. And second thing, I would like to acknowledge my collaborators that at different stages have given fundamental contribution to the work I'm going to talk about. And you can check their papers. They actually have results that go beyond what I'm going to talk today. And I believe Professor Nishimori and Shunji Matsuda will talk about related things on Thursday morning, so check out their talks. Of course, the acknowledgement for the funding agencies, and thanks to D-Wave and Lockheed Martin, which gave us crucial support to access and operate D-Wave devices. So my take-home message is the following. I would like to tell you about a very general error correction scheme for quantum annealing, which I will call nested quantum annealing correction. And the important thing about it is that it has the potential for a scalable reduction of the effective temperature of a quantum annealer. And I will explain what I mean by that. And also would like to talk about the possibility, and I would say also the necessity, to perform error correction for sampling application. And I will go through these various topics. A brief introduction about error correction and what do I mean by doing error correction by effective energy boost. Of course, I will explain what nested quantum annealing correction is, and I will give you some experimental results for optimization. Some Meanfield analysis that is good to give us some theoretical insight about the construction, and also how we can apply this construction for sampling. So, of course, the hope of using quantum computation for solving hard problems relies on the possibility to perform error correction. And we can do some kind of error correction in AQC, or quantum annealing. We have several tools at our disposal: error detecting codes, augmented with penalty Hamiltonians, some dynamical decouplings, quantum annealing corrections, which is related to what I'm going to talk about today. But still, despite all several approaches and many efforts from the community, we still don't have a fault tolerant theory in the adiabatic scheme. And the reason is that fault tolerance in AQC is hard, and the reason is because an intuitive explanation of this is that there is this tension between having effective error suppression requires non-local and Hamiltonians with very large or infinite penalties, which is in contrast with what we would like to have in practical implementation, which of course you would like local Hamiltonians with finite couplings. But still, I guess we all agree about the importance of this, so no matter if you think it's hard or if your approach is naive, you keep trying. So we need error correction in our open system, of course, and to me, a very good characterization, which is also good to have an intuition of what we are doing in quantum annealing, is this quasi-static interpretation of quantum annealing. So Mohammed talked about that in his talk and other people. So the idea is that we go through a regime where thermalization is very fast, so it's quasi-static, the system is almost in its thermal state. Then we go through a freeze-out region, and at the end of the anneal, the system is basically frozen, there is no residual dynamic. And we have several evidence of this, numerical evidence, also experimental evidence with D-Wave annealers. And the idea is that if this region is small enough, the final outcome is a snapshot of what is the approximate Gibbs state at the freezing point. And I believe afterwards, Paolo Zenarzi will talk about thermalization more, with and without quantum annealing. But again, if you accept this scenario, then you understand why we can characterize the outcomes of quantum annealers with some kind of approximate Gibbs states and determine an effective temperature for this outcome from this Gibbs states is somehow a very important parameter to understand the performance of our devices. And I would like to say that somehow a best case scenario for doing error correction in this cartoon is to obtain an energy boost for your coupling such that you can actually boost the couplings and scale this effective temperature. And if you can do this, probably as a bonus, you would get a reduction of your analog control errors. And another ingredient that we would like for a nice error correcting scheme is some kind of scalability. For example, this energy boost, we would like to scale maybe polynomially with the amount of physical qubits that we are using in the encoding. And then we try to do this with encoded Hamiltonian, and that is that your logical Hamiltonian that is defined as some n logical variables is going to be encoded and embedded in a much larger physical Hamiltonian. Of course, we have to go through some decoding procedure. And what we usually refer to quantum annealing correction is an encoding of this type that we can perform on quantum annealers of current generation. So it's a very practical approach. We really want to do error correction with devices that we have, we can work with. And the basic idea is that because of the way these D-wave annealers, for example, are built, the driver is usually not programmable and is not encodable, but we can play with the problem Hamiltonian to build up our encoding. And the way we want to do this with nested quantum annealing correction is such that we are after two goals. One, we want a general approach. And with this, I mean that it should work with a very general logical problem and with any given quantum annealing hardware. So we choose to work with complete graphs with problems we have arbitrary pairwise interaction terms. And we also would like it to give us some kind of scalability in a sense that we would like to choose the amount of physical resources we are using for our encoding with the hope to have an arbitrary amount of protection against errors. And how do we do this? We follow 3 steps. The first step is what we properly call nesting. So if we have our logical problem that is defined on some complete graph, say K4, in general Kn, we nest it into a larger complete graph. And C here is the number of times we replicate our logical variable. And in doing so, each logical coupling here is replicated many times, C² times actually, between the various copies. The local field is also replicated several times. And we need to include some ferromagnetic interaction between the C copies of our logical variables. And this is important because we want the various, the C copies of our logical variables to behave as much as possible as a single variable, logical variable. And so you see here we have this parameter C, which we call nesting level, which tunes the amount of physical resources used in the encoding. And this first step is hardware independent. You can always do this. And then next step is to actually embed this into your physical device. So if you have a D-Wave 2000Q and you are trying to encode a problem on 4 variables, you can go up to 13 levels of encoding. So there are 13 copies of each logical variable. And this is an example of how you can embed this nested encoded problem into the graph. And so you see, it's if you can see the colors here, each color represents one logical variable. You see that the physical representation of each logical variable is completely delocalized in the physical graph. And this is actually a very important property if you want this kind of encodings to work. We try other kind of embeddings which don't have this property and they work horribly. So this is crucial if you want this kind of error correcting schemes to work. And then the last step is a decoding step, which we simply choose to be a majority vote over all possible physical representation of the logical variable. So we can do some experiments with this, and because we are after some effective energy boost, it's natural to consider a problem Hamiltonian and tune the overall energy scale, here defined with alpha, and we tune this for 3 orders of magnitude. And if you run this on D with 2000Q, you get what you expect. When you use an energy scale that is as large as possible, you get success probability 1. That means that your device is always finding the ground state. And when you tune down the energy scale, it's basically increase the amount of errors. You are reducing the gaps. Thermal excitations are very strong. All the energy levels are basically going below the temperature. So basically here the device behaves as a random sampler. So you see, an obvious way of increasing the performance of your device is to increase the energy scale. But there is only as much as you can go. So what we'd like to do is to, instead of increasing alpha, we'd like to have the same effect via encoding by starting encoding our problem. And if we do that, we see that the performance of the device, the success probability of the device, grows monotonically with the nesting level, with the encoding level. And this is true apart from this region, which is a region that I call penalty limited, and I will discuss this more afterwards. It's also important to keep in mind this. So it's nice to see that this trade-off between the nesting level and the energy scale, it can be made more precise if we try to take the curves I showed in the previous slide and collapse them into a unit curve by rescaling this energy scale alpha. And this collapse somehow is our definition of energy boost, you see. And you see these curves collapse nicely over 2 orders of magnitude. And this somehow tells you that it's actually true experimentally that what you get, the performance of the device at some scale alpha after C levels of encoding is equivalent to what to get the same performance without encoding, you have to run the device at a much higher, larger scale. And actually, if you extract mu C from this data collapse, you get a nice scaling curve. We're actually interested in understanding how this energy boost scales with the amount of physical resources used. And in our construction, the number of physical variables grows like C squared. So that's what we have here. So we see this nice polynomial scaling of the energy boost as a function of the nesting level, which we again interpret as an effective temperature scaling, just because they are energy scale. They are both energy scales. So, and this is our fitting parameter here. So you see here what we are trying to do is we are solving a problem defined on 4 local variables. And when we grow C, we are using more and more physical variables. And we actually go up to 700 physical variables used for the encoding. And by doing this, we can boost our energy scales by almost 1 order of magnitude. So to understand better this scaling, as I said before, in the encoding, we use, for each logical coupler, we use C squared copies. So we expect to get at most a maximal boost that goes like C squared, but experimentally we get something that is suboptimal, it's 0.7. So how do we understand that? If we do some numerical simulation with simulated quantum annealing, we actually have an insight of what's going on. If we do simulation without minor embedding, without mapping into the device, we get a scaling that is similar to the optimal scaling. But if we do the embedding into the device, the red and yellow curves, and we introduce also noise, analog controllers, we see a scaling that is closer to what we get from the physical device. So the fact that we had to do the minor embedding and the fact that we have control errors as partially responsible of this suboptimal scaling, we think we understand that. But it's always better to have some more theoretical insight of what's going on. And Meanfield, it's a very nice tool for this kind of problem. So this is the nested Hamiltonian, written all his terms. These are all the logical couplings all packed together. These are the penalties that we need to, as I said before, to force all our logical variables, all our copies to behave as a single variable. And this is the transverse field. Now, for simplicity, I'm looking here at a ferromagnetic problem, but has all the properties that we need to understand what's going on. We introduced the mean field. One, n, call them logical mean fields. It's basically describe the orientation, the common orientation of our logical variables, and the total magnetization. And there are two phases that we derive from our mean field solution. There is a disorder phase where the magnetization is vanishing. We call it failure phase. In this phase, we cannot retrieve the ground state of the system, which is, of course, the ferromagnetic aligned state. And the phase that we call, that is an order phase, we call a successful phase, or I should say almost successful phase. But the magnetization is connected to, in fact, to the single qubit error rate through this formula. So when m is equal to 1, we are retrieving the ground state with success probability 1. And there is a second order phase transition between these two phases. Actually, if you derive the free energy, you see that the free energy follows this rescaling property, which is similar to what we have seen before. The free energy for the nested encoding C is the same as the free energy without encoding, but with either the couplings scaled by factor of C squared or by the temperature scaled by factor of C squared. So even the mean field suggests that we get a temperature scaling law that goes like C squared. Although notice that the transverse field is reduced by factor of C, and this is due to the fact that we are actually not encoding the transverse field. Something that hopefully can fix in the future with possibility to encode the transverse field. But we can derive the phase diagram for this system, and you have seen this before tomorrow. We have seen this graph before this morning, and something similar. The anneal follows a trajectory that is more or less this. And it goes through the phase transition. It goes from the disorder phase to the order phase, where you can actually have a successful computation. But I here want to get an insight of what are the possible bottlenecks for our encoding scheme. And one thing to keep in mind is, as I said before, the minor embedding reduces the performance, the scaling of our encoding. And the reason to understand this is that we know somehow that when we do the minor embedding, we introduce these chains. We need these chains to develop ferromagnetic order at the same scale, at the same time when the logical problem develops ferromagnetic order. And if we want to do this, we are forced to scale the strength of the ferromagnetic chain together as C to have the two critical points to scale with the same similarly. So the ferromagnetic penalty should scale as C, but we cannot do this because we are penalty limited, so we have to actually rescale the J's. Basically, we have to rescale alpha. And this is what as a scaling bottleneck that we see. For example, if you look at larger graphs, now I'm looking here at the K16. It's a random instance with fractional couplings, and we can nest these up to 3 times on D-Wave 2000Q. And you see here how the performance of the device increase non-monotonically in this region, which is limited by the strength of the energy penalties. But here, where we are not penalty limited, there is a monotonic improvement, which is consistent with the scaling that I was mentioning before. So, so this is actually, again, a hint that the encoding is has the potential to give us a scaling law if it's not penalty limited. If we want to use encoding for a correction for optimization problems, we really always have to compare our approach to a trivial classical repetition code. And what I mean by that is that we have to correct our performance benchmark with the amount of physical resources that we use. So an encoding of the previous problem with C equal 3 on a D-Wave 2000Q uses about 600 physical qubits. Let's say that I run it once, I get this yellow curve as a performance. Now, if I encode it only with 2 nesting levels, I will use about 300 physical qubits, so about half of the amount of resource. So I can think of running actually this twice, and then I have to take this into account, and this means that my success probability goes up because I'm running it actually 2 times. And again, if I don't do any encoding, I just have to use 80 physical qubits, about 8 times less. So I can actually, using the same chip, more or less, embedded it 8 times, and at the same time, this goes up. So again, you see that where we are penalty limited, the encoding may not be helpful, but where we are not penalty limited, actually our encoding outperforms classical repetition. And this is actually our general feature, because if we look at the same thing for an ensemble of 100 random instances, and here I'm showing the ratio between the corrected success probability with C nesting level against the baseline with this no encoding, we see that in the region where we are not penalty limited, nested quantum annealing correction outperforms classical repetition, but it underperforms when it's penalty limited. So these are the results for optimization. We can achieve this effective temperature reduction, but we have to compare ourselves to, we have to compare to classical repetition, and its advantage is reduced. So what if we actually think about using it for sampling? I would like to use error correction to improve the sampling capabilities of quantum annealers by reducing the effective sampling temperature. And if we can do that, it can be actually useful for practical applications. And we have in mind here, of course, the training of Boltzmann machines. And what we have to do if we want to train Boltzmann machine, we have to compute the training gradients, and we have positive phase and a negative phase. And to compute the negative phase, we have to sample from thermal distributions, which is a hard problem. And we would like to do this by actually sampling from the device. And that means that we would like to substitute this 2-point thermal correlation function with what we get from D-Wave devices, and to understand if the quality of the sampling we get is good enough. I think eventually this will have to be established by trying on practical application and see how well the devices perform for machine learning application. But for this talk, it's convenient to just look at how this quantity estimated by sampling with D-Wave is how close this quantity is to the thermal value. And to avoid to simplify things, I will look at this overlap, which is the scalar product of these quantities interpreted as vectors in our parameter space. If we want to do this, we have to determine a sampling temperature. And the way we do, it's simple, but it serves our purpose. We match the experimental and thermal energy histograms. What I mean is that I think about the probabilities to obtain a given state of energy E, and these are interpret this as probability distributions on the energies, and I compare D-wave histogram with a thermal histogram, and I minimize this distribution distance, and this by definition is going to be my estimate of the effective temperature of that I get out of D-wave. And of course this is going to be done is going to be computed on the logical states after encoding, minor embedding, and decoding, so it's going to depend on my nesting level. This is a very simple way to do this. There are more sophisticated estimators of the temperature. I believe that Jack Remonds is going to talk more about this. But this is a very simple approach. And we see something similar to what we have seen before. Again, a problem similar to what I showed in the optimization case. This is the estimate of the temperature as a function of the nesting level and of the energy scale. And again, we have this scaling region where we can lower monotonically the temperature, the sampling temperature of the device. And we have a penalty limited region where this temperature is not reduced monotonically, but there is an improvement here. And it's important to see that when we increase the nesting level and the size of the encoding, this overlap factor here doesn't decay. So it's a good indication that the quality of our sampling is not degraded by the fact that we are doing more complicated encoding. And actually, although there is no monotonic improvement here, this turns out this can be actually useful, because in practical application, it may be important to sample at some low temperature which cannot be reached without encoding, but we can sample at lower temperature if we allow ourselves for if we do these encodings. And so I'm looking now here at the smallest possible temperature or inverse temperature that I can get without encoding, and I'm looking at the smallest possible temperature that I can get with the 3 encodings that I can implement on the way to TSNQ. And I look at this ratio for several different ensembles of instances. We have 100 instances per ensemble on both K16, where I can do 3 levels of encodings, and on K24, where I can only do 2 levels of encodings. And these are the ratios between the smallest possible temperature and that I can get with encodings, and the smallest possible temperature that I get without encoding. And in general, you see that you can obtain reduction of the temperature, of the sampling temperature. That is, these are the medians, about 10 or 20% reduction, but in many cases, the reduction of our temperature is actually much bigger. So sampling temperature, it's typically reduced with these encodings. And again, if I look at these overlaps and how they behave, we see that the overlap is not reduced significantly. So it's a good, again, it's a good estimate, a good hint that our sampling distribution are at least as good as the one that we get without encoding. So yeah, I would like to conclude saying that nested quantum annealing correction is a general and practical approach to error correction in quantum annealing. And both experiments and Meanfield analysis suggest that it has potential to be scalable. And in fact, experimentally, we have shown that it scales well up to the wave 2000 Q size. And we show performance improvement for optimization applications, but also for sampling application. And I also discussed what are some of the bottlenecks for full scalability of this approach. Of course, this is not a surprise, finite strength for intra-chain couplings, and also the fact that we didn't encode the transverse field. It's a bottleneck for the scalability, as we understood from our Meanfield analysis. And this could be probably solved if we have the possibility of include programmable XX interaction, for example. There may be other problems which I didn't discuss, but these are important aspects to keep into account. And with that, I conclude. I would like to thank you.
Thank you, Walter. So it seems you finished a bit early, so we have time for questions.
So you've got this thing that you have to consider when you do the nesting, where you can run multiple copies in parallel. Is there an analog that you should be considering when you think about low temperature sampling? For example, if you can take 8 times as many samples, can you just resample at a lower temperature?
Yeah, that's. I don't know how to do that. So if you are able through encoding to lower the temperature of your device, I don't think you have to deal with that problem of parallel. So you are really here trading physical resources for a lower temperature. And let's say you have a sampler that works at a given temperature T, but you cannot tune this. You cannot tune down the knob. How can you use this sampler to sample at a lower temperature? You cannot do that. So if you can do this, then it's a true gain that you have.
Any further questions?
So you're able to find the temperature that minimizes the distance in the density of states, or something like this. But how good is the match? Is it actually a Boltzmann distribution?
Yeah, I mean, that's a good question. So again, you could report this distance. You know, I'm here. There are several ways, I guess, you can recover this. You can minimize this distribution distance, or you can compute your KL distance, or there are many other ways you can do that. But really, how good is good? It's a not probably a well-defined question. I think the only way to say how good is your distribution is whether you can estimate this quantity, because the problem, I mean, depends what is your application, right? So if you have in mind Boltzmann machines, then what you want to do is to compute these gradients. Now here I'm thinking about, you know, training a fully visible Boltzmann machines. These quantities are averages over your data set, and you want to get closer to this with some thermal distribution. It's really about how good is your estimate of these quantities. Of course, if you have a perfectly nice Boltzmann distribution, your estimate of this is going to be good, but maybe you can get a good estimate of this without being too precise with your sampling. I mean, so I think that's why I said before, eventually it's going to be about trying this on applications and see how well it works. But of course, your goal should be to get a distribution that is as good as Boltzmann as possible, right? Because that ensures that you are computing the right thing. That's why I didn't put a number like a distance, because it may not tell you much, right? Here, I wanted just to say that at least from this very simple quantity, you don't see a degrading of your distribution. But
okay, maybe time for one more question. There's none. I might add a simple-minded question that sort of always lingers when I see error correction in the context of quantum annealing, is if we at least one resource that is often, of course, invoked when doing annealing is tunneling, finite range tunneling. So in any error correction scheme of this sort, you add extra variables. So now that increases the action for the tunneling transition, and therefore tunneling will be suppressed. Shouldn't this ultimately hurt your success probabilities?
Yeah, I think so. This is somehow related to the fact that, okay, I should go back. It's somehow related to the fact that we are not encoding the transverse field. So you think of the transverse field as what drives your tunneling rates, right? And you see from here, at least this is it's a static, it's a thermodynamic, it's equilibrium quantity, right? It's the free energy, but you have a scaling of the temperature, which is something that you like, but the transverse field is rescaled, it goes down. So you see from here somehow a manifestation of what you probably have in mind. And also, I have only discussed here a hint, or Meanfield gives us a hint about the equilibrium of the system, but eventually you have to remember we are going through a freezing phase and a frozen phase, and of course when the size of the system grows, we expect this freezing to happen maybe earlier. That means at higher temperature. So there are all sorts of dynamical questions here that you have to take into account, and they can also make this scaling worse. Okay. But so what you're saying is because now I have a lot of physical qubits, I have my minor embedding chains, and I have to tunnel the whole chain, all at once to go through
Energy
to
barrier.
find the ground state, to go through our energy barriers to find the ground state, and that can be suppressed because of the size of the system. But that's like an intuitive. Intuitively, it's going to happen, but
But yeah, you're right. I mean, this correct observation that if you could track of time, but if you could act on the transversal field as well and make it stronger to keep up with the encoding, then you could reverse that concern that I just voiced.
Yeah.
It takes this microphone.
So in the Meanfield analysis, which is in one of those papers with Matsura et al., we looked at what happens to tunneling in the free energy landscape. And it turns out that this encoding both reduces the height and the width of the tunneling barrier. So there's
specific ones with the nested version.
Yes, yes. So it's not clear that tunneling is suppressed. On the one hand, as Walter is saying, the transverse field is non-coded, therefore you get less quantum fluctuations in some sense. On the other hand, in the free energy picture, the tunneling barrier is smaller.
I see. Okay.
Yeah,
that's interesting. That's not.
Yeah, all the Meanfield analyses are done before manual embedding, and while all the experiments are done on the physical implementation. So there's always this thing to keep into account, to keep in mind. All the Meanfield is done here, but all the experiments are done here. So there is an intermediate step to keep in mind. Yeah.
Okay, I think we need to stop here, and thank you one more time, Walter.